Welcome to Numerical Methods for Scientists and Engineers. Video 7. Decomposition Methods. Doolittle LU Decomposition. Decomposing a matrix into LU form offers several practical and computational benefits in linear algebra. A matrix is decomposed as A equals LU, a lower triangular matrix L, and an upper triangular matrix U. LU decomposition simplifies repeated solutions of a matrix equation. Once a matrix A is decomposed or factored into its LU form, it can be employed to systems with different right-hand sides very efficiently. LU decomposition avoids the need for direct matrix inversion, which is expensive. The determinant of a matrix A can be found as the product of the determinants of the matrices L and U. Since L and U are triangular matrices, their determinants are simply found by multiplying the elements along the main diagonals. Once the LU decomposition, or LU factorization, is obtained, solving for X requires only forward and backward substitutions. Substituting LU into A and defining the U times X product as Y leads to two triangular systems of equations, UX equals Y and LY equals B. Of these, LY equals B is solved using the forward substitution algorithm. On the other hand, UX equals Y is solved using the back substitution algorithm. Doolittle LU decomposition method factors a matrix into a lower triangular matrix L whose diagonal entries are 1s and an upper triangular matrix U. Kraut LU decomposition factors the matrix into a lower triangular matrix L and an upper triangular matrix U whose diagonal entries are 1s. Cholesky decomposition method is applied to matrices that are positive definite, non-singular, and symmetric. Matrix A can then be decomposed as A equals L times L transpose. The Doolittle decomposition can be applied to symmetric or non-symmetric matrices. The goal is to decompose matrix A into a lower triangular matrix L and an upper triangular matrix U. Assuming that the LU decomposition for a general n by n matrix A exists, we can systematically use the equations from the multiplications required for A equals L times U to solve the entries in L and U. Comparing and matching the multiplied LU matrix with the matrix A, we determine the elements of L and U. Comparing and matching the first rows of A and LU, we observe that the first row of matrix L should be set to that of the first of matrix A. That is, U1j's are set to A1j's for j equals 1 to n. This process gives the first row of matrix L. Next, we set L1 1 to 1. Comparing and matching the first columns of A and LU, we obtain the first column for I equals 2 to n as follows. The procedure is sequenced to compute one row of U and its corresponding column of L until all rows and columns of A are exhausted. The elements of the ith row of matrix U and ith column of matrix L are determined by row and column sweeps and can be generalized as follows. The Doolittle method has the following advantages. The method is relatively easy to understand and implement. It is numerically stable. It does not need the information on the right-hand side vector B. It is CPU time efficient when solving AX equals B sub M for M equals 1, 2, and so on. Having L with 1s as the diagonal elements guarantees the uniqueness of A equals L times U. However, the method comes with several drawbacks as well. Employing it to get a one-time solution of a linear system is inefficient due to excessive calculations devoted to decomposition, forward, and backward substitutions. Memory requirement increases by twofold if L and U are stored as separate matrices. Every square matrix is not LU decomposable. If A is reducible to the row echelon form with Gaussian elimination without ever interchanging two rows, the matrix A has an LU form. For large matrices, the round-off error emerges as the main drawback of the decomposition methods. Using two triangular matrices, L and U, in the algorithm given here doubles the memory requirement. Nonetheless, as illustrated below, the memory requirement can be minimized by storing L and U in place of A. That is, overwriting the original matrix and omitting the storage of 1s and 0s for L or U, as they are the givens of the method. Consider LU decomposition of the following 4x4 matrix. We start with the first rows of matrices A and U, and set the first row elements of A to those of U. Next, we compare the first column elements below the diagonal. U11 has already been found. Thus, we can obtain the elements of the first column of matrix L as follows. We move on to the second row of the matrix U. The elements of U and L21 are known. We can then obtain the elements of the second row of U as follows. Now we move on to the second column of L. We will calculate the third and fourth row elements. The required elements of matrix A and L have already been calculated, so we obtain Then we advance to the third row of U to determine U33 and U34. The elements U have already been computed. So using this relationship, we obtain the following values. Now we will move on to find the third column element of L, L43. All required quantities in the relationship given are available, so we find And finally, the fourth row diagonal element of U, U44, is calculated as follows. This completes the decomposition procedure. We now have the upper triangular matrix U and lower triangular matrix L. That is all for now. See you next time with another topic. Bye.